Welcome. Today we look at limits. It's a subject which mathematicians have thought about for thousands of years. Zeno was one of the first who thought about it, Greek philosopher and mathematician. Archimedes made some headway, but only in the 19th century the modern notion of limit really was created. And we write like that. We write limit x goes to a, f of x is equal to b, meaning that when x goes to a from either side, that we reach the value b. Kind of something like that. It's a function, this is a, this is b, and we should have something like this. So maybe we don't know the function at the value a, but what happens is when x goes to a, so that x, and that's y, when x goes to a, then this function value should reach the value b, and it also should be the same value when we come from the right hand side. So area computation, length computation, volume computation, but also evaluate functions at places where they are not defined a priori. And that has to do with healing broken bones. I use this terminology also because algebra means healing broken bones. And one of the places where this really kind of appeared first is in algebra. If you have a function like x squared minus 1 over x minus 1. So this is a function which is defined everywhere except at x equal to 1 because we divide by 0. And what we want to know is what is the limit at x equal to 1. So there is no problem to evaluate this function at any value different than 1. For example, we see that at x equal to 0, that's minus 1 over minus 1, that's equal to 1. At x equal to minus 1, so that's the point 1 where we really don't know the function. At minus 1 we get 0 because that's 0. At minus 1 that's minus 2, so that's still 0. And at 2 we can also evaluate it. Let's see, at 2 we get 4 minus 1 is 3, 2 minus 1 is 1, so we have 3. At 2 we have 1, 2, 3, so maybe here. The function value was here. And if you use a computer and plot that, or you do by hand, you compute more values, you see that's actually a very nice function here. We don't know what happens here at the point 1, but it continues like that. If you draw that, you will see there's no problem. But it's a broken bone here. Now, how do you fix that? You might actually see that what happens here. If you know a little bit of algebra is the healing of broken bones. If you know a little bit of algebra, you know that's x minus 1 times x plus 1. So you can actually factor that out. So it's x minus 1, x plus 1, and then we divide it by x minus 1. And now we can delete this problematic part, and we get just x plus 1. So if you look at this function y is equal to x plus 1, that's everywhere a line, right? That's this line here. It's perfectly fine. Everywhere perfectly fine. At x equal to 1, we had originally not a defined value, but there is a limit. There is a limit when we come from the left or when we come from the right. We actually get the perfect limit here. And you see the limit because you know the function here, the limit should be 1. So this is at 2, we know the limit is 1. So what we do is we write the limit when x goes to 1, x squared minus 1 over x minus 1 is equal to 2. In this case, a was 1, b was 2, and we have a perfect answer. And this is a fact we can verify algebraically. But understanding this limit essentially will lead to the understanding of all possible limits, because this is very typical and it's also very applied. This is a very important function. This function is also called the sinc function. And it's used in information theory, communication theory. Here, Shannon, Whittaker, and so they have worked on information theory, and there this function appears. It appears in number theory. It appears in many places. So, and what we want to understand is what happens at x equal to 0. So this is a little bit puzzling, because we cannot plug in x equal to 0. We can also not just divide out something like before with the healing of broken bones. So there are different meanings which we can, how we can interpret this problem. You know the sine function. So if you look at the sine function, it's like that. And so if you take x here, this is sine x. And this is x. So what we actually do is, this is called the average rate of change from here to here, is the slope, sinus x over x. So this is a sinus of x over x is the slope of this secant line here. So that's sinus x over x. And that's the reason why it's so important in trigonometry, because it will allow us to see what actually, when we take the limit x goes to 0, if we make this triangle smaller and smaller and smaller and smaller, it allows us to see what is then the slope of this at this point. And that's one of the fundamental things in calculus, to understand what is the instantaneous rate of change. So it will lead us to a very important thing. It will lead us to the derivative of the sine function. So what we will do next week, derivatives of sine of x. So that's one of the motivations. Another motivation which comes in here is the computation of the, so let me just put that here. Here the motivation is to compute the area or the circumference of a, this is x here. So this is actually what we have, and this is 1, this is sinus x. So when you make a polygon approximation, if you make a polygon approximation of the circle, that's what Archimedes did, and so this is actually just 2 times sinus x. And 2 times sinus x. And so what we will do when we compute the circumference is adding up all these lengths. When you plot it with a computer, you see this function is 0 at 0 we don't know, but at pi it's definitely 0. At minus pi it is equal to 0. At 2 pi it is equal to 0. At minus 2 pi it is equal to 0. So this function looks a little bit like the sine function, but then it gets damped by x. So which means that it kind of goes down somehow like that, and then so like that, and then it will do something like that. And also here, this is an even function. So this is an even function. Kind of looks on the left exactly the same. So what we can do when we investigate this numerically, we can go here closer and closer to 0. And here you see already kind of the insight which you see when you look at the graph here. You kind of see the slope is getting to 1, and actually this is happening. And this is at this point we really don't know the value yet. But what we have is we can actually verify that the limit x goes to 0, sinus x over x is equal to 1. So let me just actually write it like that. So that's the theorem. I can actually explain that here, why this is true. We also want to see kind of why it is true, and that is an analysis which already Archimedes was was working on. So let's just look at the definition of the sign So we have the unit circle here. If this is x, I drew that already last time when we talked about the sine function. We will talk a lot about the sine function. Then this was sine of x. So this was 1. This was sine of x. And then you might know from geometry, right? The circumference of the circle is 2 pi. The angle is 2 pi. So this is actually just proportional to x. So that means the length here, the arc length is x. So when you have a circle of radius 1, the arc length is exactly the angle. So that's equal to x. So you see, we compare this length with this length. And you can already see that they are essentially the same length, right? Because what happens if these get smaller and smaller and smaller? They get closer and closer together. But we can justify this a little bit better. And we have also seen the tangent x here. Also mentioned that last time. This is the tangent x. And so if you look at this picture, you see that the x is sandwiched between sinus x and tangent x. So what we have is the smaller thing is sinus x, and smaller than x, smaller than tangent of x. Now, that's what we just see when we look at this definition, and then we divide by x. So we have sinus x. No, we divide by sinus of x. That's the key. We divide by sinus of x. So we divide by sinus of x. So what we do is we divide both everything by sinus of x. So let's do that here. Divided by sinus of x, divided by sinus of x, divided by sinus of x. Right, we can do that for positive x. So what we have is 1 smaller than x over sinus x. And if you remember what the tangent was, right, tangent x is sinus x over cosine x. And if you take the tangent of x and divide by sinus x, you get actually just cosine 1 over cosine x. Right? So that's 1 over cosine x. Secant x. Now we have sandwiched that between 1 and 1 over cosine x. But cosine x, so that's 1 over cosine x. 1 over cosine x has no problem at x equal to 0. At x equal to 0, this is 1 here, so this goes to 1. So now we are done, because now this is actually when x goes to 0. This is already 1. This goes to 1. And so this is sandwiched between two things which go to 1. So also that goes to 1. So that's the argument which tells you why this result is true. So it turns out if you know this limit, you know all the derivatives, you can derive all the derivatives of all the trig functions from that using a little bit of theory. So that's a very, very important limit. Prototypical, it's a prototype. It's also important in application. For example, in information theory, sampling theory. But before we come to the history, just one example. I just make one example which covers a lot of ground. What is the limit x goes to 0 of sinus 3x 5x? And so that's what is that limit? Now we can use this theorem. We don't have to go through all the machinery again. So that's so how do we do that? So one of the things is we use a trick here. So we just write So we can just write it as sinus 3x over. We know that, right? We know when we take sinus 3x over 3x, that's like sinus y over y, or sinus u over u, if you take another variable. We know what happens with the limit x goes to 0. But then we have to multiply by 3x over 5x. So there's a little trick here. And this is actually just 3/5 here. This is 3/5 whenever x is not equal to 0. We know that this is actually going to 1, right? Because of the theorem. And so we know that the answer is equal to 3/5. Okay, let me just say something about the concept of limit. Historically, so Zeno was just long time ago, 2,500 years ago. He was looking at the paradoxa. And Zeno paradoxa, a fundamental way, invoke the concept of limits. So, for example, when we look at an arrow flying, and we want to see, we have a trajectory of an arrow flying, we will come to this. What is the velocity of that arrow? But or how does it move? But at every moment of time, the arrow is fixed, so it cannot move. And so this was one of the things which was not resolved. And then Archimedes was able to compute the area of the circle by just approximating it from inside and outside with polygons. So this is an example of his computations. He got to the value of pi, at least to approximations of the value of pi, and also he was able to do the volume of the sphere. So pi r square, r cubed. Also the arc length here. So this is the area, and then the length was 2 pi r. That's all Archimedes. Or here, the surface area. This is the volume. The surface area 4 pi r square. It's the surface area. So all these computations which involve pi. So all of these computations involve the number pi, and pi is not a number which you can get. Ultimately, you cannot write down the ultimate way to write this down. So it would involve infinitely many digits. So this is not a rational number, and so Archimedes kind of got an approximation, right? And engineers use the approximation pi is equal to 3. So you can use various approximations. The computer has built-in approximations, maybe with 17 digits. But one knows it for millions and millions of digits. So that's Xenodachimatus. And then we will come to Bolzano and Cauchy. So that's in the 19th century. Very interesting time, very beautiful time. Today we work on calculus versions. There are calculus versions which don't invoke any limits. So this is quantum calculus. Where you never actually then take limits. So you would, for example, write fx plus h minus f of x over h. And that limit will be, next week we will see that that's one of the major motivations to look at limits. That's why we introduce it also. That will be called the derivative. But in quantum calculus, you don't care. So in quantum calculus, what you do is you actually don't take the limit, and then h is a small number. Maybe Planck constant size, or Actually, when you develop the mathematics, you don't care what age is. You just work with expressions like that. So that's it for today.